Welcome back, everyone. In today's lecture, we are going to discuss the dynamics of a seismically isolated structure under the action of earthquake excitation. So, we are first going to learn how to represent a seismically isolated structure in terms of a multi-degree of freedom system, and then look at its frequencies and the important parameters that actually define a seismically isolated system, and then further discuss how those parameters actually represent the behavior in terms of its dynamic characterization. Okay, and what are the important things that need to be considered in the analysis of a seismically isolated building. Okay, so let us get started.
So let us basically start with a very simple formula that we have been using and utilizing again and again. What we said, and that you already know, that the time period of any structure, we said that it would be 2 pi m by k, right? We have been utilizing this to understand the concept of base isolated structure as well. Now, what is the inherent assumption here in terms of the degrees of freedom? Like if I'm writing this formula, what can I say about the degrees of freedom for the structure that I'm writing this formula? Can I say it is a single degree of freedom system, only valid for single degree of freedom system? Okay, or a simple representation could be this mass stiffness, and if you want to put damping, that's fine as well. Or so this is the spring mass damper representation, or if you want to write in terms of frame representation, then you may consider this interpretation. Okay, this is your U. So the horizontal stiffness is represented by the overall stiffness of this frame. Okay, and basically you can have ground motion here. Okay, now what happens during an earthquake? You would have a ground motion like this. Okay, so in both direction. Now we said that this is the formula we are going to use, but as you might imagine, in reality, basically no base isolated structure, okay, would be a single degree of freedom system. So in the end, this is an approximation. Okay, and like any approximation or assumption, it is valid for certain cases. Okay, and this works out to be good for base isolated structure because of the nature or the relative flexibility of the isolation layer. Okay, would not be valid for any other type of a structure unless you have, and that is what we are going to look in today, that when would it be valid, this single degree of freedom representation, and if it is not valid, can we do a simple analysis of 2 degree of freedom system so that we understand how the superstructure and the isolator basically behave, how and what kind of basically participation do they have in the overall response. Okay, so those are the things that we are going to look into today. And before we do that, I will just quickly go through some concept and brush up some of your concept of, and you might already be aware, but we will do that anyway, of earthquake excitation, okay, of a single degree of freedom system and a multi-degree of freedom system. Okay, so as you might know, okay, if let us say I have this frame here, okay, and I have this mass here. I'm assuming that the whole floor mass is actually concentrated at this level. Now, due to earthquake, there would be a ground movement. So the whole structure will move with the ground, right? And then there would be relative deformation in the structure. So first, there would be a rigid body motion of the structure due to ground movement. Let us say this would be UG. which is basically the displacement of the ground. Okay, and we are representing the ground motion as ground motion acceleration history at ug double dot t. Now, then we would have this deformation here. Okay, and let us say this mass moved here. So this relative deformation we are going to denote as the deformation of the structure. This is the deformation of the ground and this is the total deformation ut. So basically ut is ug plus relative deformation of the mass. This mass we are considering. So remember, the degree of freedom that we are representing, we are saying that this whole frame can be represented as a single degree of freedom system if, okay, if there is no axial, basically actually if the member are very rigid, so that whatever this node is going through, actually the same is would be going through the right node. Okay, and the overall, if we consider the lateral deformation is what contributes to the, or what denotes as the degree of freedom. So the total displacement of the mass is ug plus u. Okay, and if you want, the total acceleration would be, you can differentiate it twice, it would be this. Now if you want to write down that basically the equation of motion for this one, we know that you can perhaps cut this structure here, okay, and write it. Okay, so if you consider the free body diagram of this, okay, acceleration is always total acceleration, okay, but deformation or the force in the frame is due to relative deformation. Okay, because of rigid body motion of the structure, it does not basically induce any internal forces. Okay, so the internal forces would be whatever the relative or the lateral stiffness of the structure is. Let us say this is K times the relative deformation. Okay, and there is no other force. Remember, whatever force that is being applied, if you're thinking from the ground, that is coming into this total acceleration. So the equation of motion that I will get is basically this here. And if you substitute ut is equal to this quantity here, you can further write it as mu double dot in terms of relative ku is equal to minus m ug double dot. Okay, and this is basically your effective earthquake force. So I understand many of you already aware of this, but I'm just repeating it for the sake of completeness. Okay, so this is for a single degree of freedom system. And if you had a damper, okay, you could perhaps include that as well. So this is the undamped system, but let us say you had a damper like this. So remember, damper also depends on the relative velocity in the structure between the points, okay, between the points of connection of the damper. So then you could perhaps write this as Cu Ku is equal to minus Mug. Okay, and this quantity here, the Cu basically relative damping force and the stiffness force, these are all depend on the relative deformation and relative velocity. Okay, but acceleration we included as total acceleration because it is always measured with respect to inertial frame. So this is our equation of motion for a single degree of freedom system. Okay, if you understand this, then we can perhaps write it for a multi-degree of freedom system as well. Okay, so let us say I have a multi-story shear type building. Okay, the assumption in a shear type building is that the flexure deformations, okay, are small. The axially members are rigid. So overall, we can represent the degrees of freedom by deformation at each floor. Okay, so this is a shear type building. Okay, now let us say masses are again concentrated here. This is M1 and this is M2. Okay, and you can have again forces UG, basically ground motion, ground acceleration UG double dot applied like this. Okay, so like what we had done for this, we can also write down the equation of motion for this by considering equilibrium of the masses one at a time. So if you consider the equilibrium of mass m2, which is at this position, okay, the relative and let us say story stiffnesses we are considering as k1 and k2. So the force here would be in opposite direction of deformation, which would be u2 minus u1, because story stiffness is k2, so the net force would be k2 times the story drift, which would be u2 minus u1. Okay, and again this would be the total acceleration, so it would be m2 u2 double dot plus ug double dot. Okay, similarly for the first story, if I consider like this, the force from the top would be equal and opposite to the force that you are applying here. So this would be q2 u2 minus u1 in the opposite direction, and below it would be k1 due to story, first story, and then u1 minus this, which would be basically 0. Okay, and the inertial force would be m1 u1 plus ug double dot. Okay, so we can write down separately the equation of motion for each of these. Okay, it would be m1 u1 plus m1 ug double dot plus k1 u1, and this would be minus of k2 u2 minus u1, that should be equal to 0. So what you will get basically m1 u1 in this side plus k1 plus k2 u1 minus k2 u2. So this is for first story. Okay, similarly for the second story, if we consider the equation of motion for this, we can write it as, and remember there is another term here that I have brought from this side, it is minus m1 ug double dot. Okay, so for the second story again it would be m2 u2 plus ug double dot plus k2 u2 minus u1, and that is equal to 0. So it can be further written as m2 u2 plus, or let us say here it would be minus k2 u1 plus k2 u2 is equal to minus of m2 ug dot. So this is second story. Now you know that this both equation can be combined as a single matrix equation. Okay, if you combine this, basically this equation here and this equation here, okay, these can be combined and written in a matrix form as the coefficient of u1, which is m1 0 0 m2 times u1 u2, and then the stiffness matrix, which is basically k1 plus k2, this term here, minus k2, again minus k2, and this is k2, and u1 u2, and this is equal to minus m1 0, basically this is minus m1 minus m2, and this is ugt. But we can further write this as in terms of mass matrix m1 0 0 m2, and then another vector which is called an influence vector 1 1, and then ugt. You will see that it is the same quantity. So my final equation of motion is m1 0 0 m2 u1 u2 plus k1 plus k2 minus k2 okay. So like we did for a single degree of freedom system, we can generalize the same equation for a multi-degree of freedom system as well, where this is mass vector m times the acceleration vector u double dot, then the stiffness vector k times the displacement vector u, and this is equal to again the mass vector m, mass matrix m, and then the influence vector L, and then UGT. Okay, and this is the equation of motion for multi-degree of freedom system. Now, for a single degree of freedom system, we did not have any concept of contribution factor, okay, or anything, because there was only one mode. But as you know, for a multi-degree of freedom system, okay, basically it is represented by different modes, and the overall response is basically sum of the contribution of response due to each mode. Okay, and that becomes important because let us say your structure has multiple modes. Okay, multiple modes also means that multiple time period or frequencies, and dynamic behavior when you try to predict, you very well understand what happens to a single degree of freedom system when it is applied to different type of load. For example, harmonic load, earthquake load, it is much easier to visualize, but it is not so easy for a multi-degree of freedom system. Okay, because you have multiple modes with multiple frequencies, and if you say that the overall response is governed by a typical mode, then you need to know how much is that mode is contributing and what would be the effect of higher modes. So all these things are like, you know, topic of interest if you start to go much into the dynamics of it, but we can rely on that to explain the behavior or the multi-degree, basically multi-degree of freedom representation behavior of a base isolated structure as well. Okay, and we are going to use the same concept, extend it to base isolated structure, the equations that we have derived. Let us see what happens to a base isolated structure. We said that till now we have considered base isolated structure to be a rigid mass, okay, on top of any spring or anything, or if you want to draw like this, perhaps this would be a good representation. This is the superstructure mass. This is the isolator stiffness in the horizontal direction. Although I'm drawing it horizontally, this is spring mass system. In reality, what I'm saying, you have a base isolated building, let us say like this, and you have multiple isolator, let us say. Okay, and we assume it to be almost rigid. This is a single mass, and because it is rigid, whatever like displacement you take here, the same is the displacement here. So we say that let us assume the displacement as u, and that to be the degree of freedom for this base isolated structure, and the horizontal stiffness is basically the stiffness of the isolation layer. Okay, and then we say that, so this is a SDOF representation. Okay, and then we say that Tn would be 2 pi under root m by k, where m is the mass of the superstructure. Okay, remember that. Whereas k is stiffness of isolation layer, not the superstructure. But as you can imagine, in reality, superstructure would not be rigid, right? It would be, it would have some finite flexibility. And it is important that we take that flexibility into consideration to completely understand the behavior. Okay. So let us do that. Let us see how do we do that. So what I'm going to draw here. Okay. Let us say I had a base isolated structure in which superstructure is being represented by this frame. And then there are isolators, which I am representing through these two isolators. Okay. And basically this mass here, let us call it MB, which is the mass of the base mat. Okay. And MS, or let us just call it M. okay, which is the mass of the superstructure. Okay. So mass of the basement and the mass of the superstructure, and we are assuming that all the column mass, everything has been lumped with this superstructure mass. Now the stiffness of the isolation layer, I will denote it as Kb. That is the stiffness of the isolation layer. And the damping coefficient of the isolation layer, let us say Cb. Similarly, for the superstructure, the total stiffness of the superstructure, let us say, is damping is Cs and the stiffness is Ks. Okay, and this isolation is fixed at the ground and it is connected to this basement, and there is a ground excitation. So now this is a 2 degree of freedom representation where we are going to represent, okay, deformation at this level and deformation at the superstructure level to represent the displacements at the isolation level and the superstructure, okay, to represent the overall behavior. Now again, of course, in reality it won't be a 2 degree of freedom system, but a 2 degree of freedom system is a much better representation in terms of understanding the dynamics or the contribution of superstructure and isolation. So the overall structure I'm dividing between the isolation layer and the superstructure layer, okay, and I'm trying to study the dynamic behavior of that. Okay, so let us say under the action of this ground motion, what will happen? First, initially if the structure was here, okay, there would be some ground movement. So this is the initial position of the structure. Okay, the ground movement, let us say it is UG. Okay, that would be the rigid body motion of the overall structure. Then there would deformation at the isolator level. Let us represent it through this deformed shape. And we will say that this deformation is actually VB. Okay, let me write it here. This is V of B, this deformation here. Now the superstructure would also have some relative deformation. Okay, so let me just write it, draw it here. And this relative deformation, let us say Vs. Don't go by the scale because Vb would typically be much higher than Vs. Okay, but just for the sake of drawing, I have drawn it like this. So Vb is the relative deformation at the isolation layer with respect to UG or with respect to ground, and Vs is with respect to the isolation layer. Okay, I hope there is no confusion here. Now we wish to write down the equation of motion again similarly for this one, and it is up to us how do we write down the equation of motion. So what I'm going to do here in this case, first I'm going to write down the equation of motion of this whole system, the whole structure, and in the second case I'm going to just write down the equation of motion of the upper slab. If you wish, you can do isolation layer at one time and then the overall or the top layer at other time, like we did in the previous cases. But for this cases, from the mathematical manipulation point of view, it is much easier for me if I first write down the equation of motion for the whole structure and then the top slab. But in the end, because there are 2 degrees of freedoms, basically you would only get 2 independent equations. Okay, not more than 2. So it doesn't matter how do you choose to write down the equation of motion, you would still get only 2 independent equations of motion. Okay, so let us first consider the whole structure and consider the free body diagram of the whole structure. Okay, so when I say the whole structure, I mean the whole superstructure. Okay, this is the mass M, this is the mass MB. Okay, now if I consider the free body diagram of this, and basically I'm cutting the structure here, the elastic forces would be due to the isolation layer only, right? And that would be Kb, which is the base isolator stiffness, times the relative deformation of the isolator, which is here Vb. Okay. Now my structure is moving right, so I have to apply inertial forces. Okay, and if I apply the pseudo forces, it would be opposite to the direction of motion. So for the top mass, it would be mass times total acceleration. Now the total acceleration would be Ug plus Vb plus Vs, okay, due to each of these three quantities. So it would be Vb plus Vs plus Ug acceleration. And inertial forces on the mass below Mb would be Mb Vb plus Ug. Are there any other external forces that are acting on it? No. I mean, because we are considering damping now, we also need to consider the damping force here in the isolation layer. And it would be simply Cb times the relative velocity, which let me denote by Vb dot. Okay. So if I write down the equation of motion for this one, okay, let me just write it down. M Vb plus Vs, remember this is acceleration here, plus Ug plus Mb Vb plus Ug plus Cb Vb dot plus Kb Vb is equal to 0. Now I need you to do one thing. I have written down for the whole structure. Now what do? You just cut this structure at this point, only the top, basically the superstructure, and then similarly draw the free body diagram and write down the similar equation of motion for the top layer. Okay. Once you're done with that, like we did here, combine the whole thing or write it the whole two simultaneous equation like this in terms of matrices. Okay. Remember, on the left hand side, the acceleration vector or the displacement vector that we are looking for is V equal to Vb and Vs. Okay, and the acceleration vector basically would be V double dot is equal to Vb Vs. So accordingly, you have to arrange equations like we did for this and write it like that. Okay, let us discuss the solution now. Okay, and we'll compare. So we have already written this for the whole structure. Now we can, let us say, just isolate just draw the free body diagram of the superstructure. So for that, if you consider the superstructure, let us say this is my superstructure. It would have basically inertial force opposite to the direction of excitation, or the pseudo inertial force opposite to the direction of excitation, which would be Vb plus Vs, because this is the total displacement and we are differentiating it twice. Okay. And then it would have, because of the superstructure, so we are considering only relative deformation, so it would have Ks times the Vs, because Vs is the drift of the superstructure. Similarly, the damping force as well, Cs times Vs dot. Okay, so we can write down our equation of motion for the superstructure as, let me just M Vb plus Vs plus Ug plus Cs Vs dot plus Ks Vs. Okay, and let us now further write down these two equations so that are they can be written in the matrix forms. To do that, what I need to do, combine all the terms which are multiplied by Vb dot acceleration term, Vb double dot and Vs double dot together, and same for the displacement, and then see what do we get. So here I would get as M plus Mb times Vb plus m times Vs plus Cb Vb dot plus Kb Vb, and I need to bring this term on the right hand side, which is minus m plus mb, okay, times Vg, sorry, Ug double dot. So the ground acceleration term. Similarly for this, I can write mvb plus mvs, okay, plus cs vs dot plus ks vs, and the ground motion term I am going to bring it on the right hand side. Sorry, not this, Ug double dot. So these are the two equations that I want to combine in the matrix form. Okay, and if I do that, what would I get if I write it in the matrix form? This coefficient, and then this and this coefficient. So it would be m plus mb, and then m, and then m and m. Okay, and it would be vb double dot and vs. Similarly, cb 0, 0, cs, vb dot, and then vs dot, plus same as kb 0, 0, ks, vb vs, and this is equal to minus of m plus mb, and then here it is m, and then it is multiplied with ug. Now like we did previously, we can further write down this as minus of m plus mb, then m, and then m and m, which is the same as the mass matrix. So I'm trying to write it same in the mass matrix term, and this I will write it as 1, okay, and 0, because influence vector, if you look at it, if you multiply this vector with this matrix, then I will get this vector here. Okay, so this is my equation of motion with the mass matrix as, let me write it here, mass times acceleration plus damping times the velocity vector plus the stiffness matrix times the displacement vector, and this is equal to mass, influence vector, and ug, where the mass vector and everything is again, and damping matrix all are shown here. Okay, so this is the multi-degree of freedom equation for my base isolated system. Okay, and this is what we need to solve to find out the frequencies of the base isolated structure and the superstructure, or like different modes, sorry. Okay, and the participation factor and everything. So this is what we are going to utilize. But before we get into that, let us define some useful quantities. Okay, so we say that, remember, whenever we talk about a fixed base building and base isolated building, we always compare the frequency of the fixed base, okay, fixed base superstructure or the building to the base isolated structure, isn't it? We say that if the fixed base frequency is, let us say, 1 hertz and the base isolated frequency is 0.0 hertz, how do they how they basically contribute to the overall response? So that's why we always talk in terms of the fixed base building and the base isolated building. Okay, so what I'm going to do here, I'm going to consider the superstructure as a fixed base with mass m, stiffness ks, and this is a single degree of freedom representation of the basically the superstructure. So for this, I know that for the fixed base superstructure, I can find out the frequency as ks divided by m, and damping as cs divided by 2m omega s. Similarly, for the base isolated structure, I am going to define, this is my base isolated structure, right? If I consider not a single degree of representation now, sorry, not a 2 degree of representation that I have considered above, but a single degree of representation. Okay, just for the argument. Why I'm doing that, I'll come back to that later. Okay, with the stiffness Kb here, and the overall mass of the superstructure would be now what? It would be a capital M, which is M plus Mb, mass of the superstructure, and this one. So when I consider a single degree of representation of the same building that I've been doing a 2 degree representation, I can write that the frequency as omega b equal to Kb M plus Mb, right? I hope you understand all of the formula that we are doing. So we are going to write this as Kv divided by M, where M is now the total mass of the superstructure. Remember, initially when the structure is not isolated, you only have M. But when you need to isolate the structure, we need to provide an additional base mat here, like we discussed yesterday and the day before that in the class. That for the base isolated structure, you need to have either a rigid arrangement of plinth beam, okay, or you can provide a very rigid base mat. Okay, so what do you have here is Kb M plus Mb is equal to Kb divided by M. Okay, where M is the total. Now these are the two frequencies that we are already discussed, that what would be the frequency of the superstructure and the base isolated structure. But when we consider this equation and 2 degree of freedom representation, now we know that from this we are going to get two frequencies, omega 1 and omega 2, right? Because it's a 2 degree of freedom system. Can you tell me, would this omega 1 and omega 2 be same as omega s and omega b? What do you think? Remember, these are not the modal frequencies. Okay, these are not the modal frequencies. These are just the frequencies of these two structures that we have defined. These are not the modal frequency of 2 degree of freedom system. It won't be same. Okay, although it might be close depending upon some situation, like some parameters, but this is a 2 degree representation with frequency omega 1 and omega 2, and these are two separate structure. A superstructure that has been considered as a single degree of freedom system, so we've got this frequency, and then the whole base isolated structure that I have again got the frequency as, okay, when we consider 2 degree of representation of the same building, okay, we know that we will get frequencies omega 1 and omega 2. I don't know what this frequency would be. Okay, what I have done below here, I have considered two single degree of freedom system. Okay, remember this is the same system. The second one, this one here, is the same system as above, but now being considered as a single degree of freedom system. Okay, so in general, this single degree of representation frequency, would it be same as the multi degree of freedom system frequency? If you consider a frame and then you consider as a single degree of freedom system, or if you consider a multi degree of freedom system, would the corresponding frequency of both these two would be same? What do you think? Now we have considered in the 2 degree of freedom system the flexibility of the superstructure. Like in this case, when I am considering single degree representation of the same structure, I am considering this whole thing to be rigid. I am saying that there is no relative deformation, so there are no forces generated because of this one, and the overall basically response of the system, I can represent it through the deformation at the isolation layer. But above, I'm not doing that. So in general, the frequencies of this and of the 2 degree of freedom representation and this 2 single degree of representation system won't be same. Okay, but we will see that for base isolated structure, it might be close. Okay, because of some parameters or some because of the inherent property of the isolators that we use. We will see that how do we do that. Okay, if omega b is closer to omega 1, then we can say that the very first approximation that we had considered, it's a good approximation. In this case, what is m here? M plus mb. and K here is basically KB, right? Okay. And why that is a good representation? It depends on the frequency ratio. We'll come back to that. Okay. So in general, can I say stiffness of the isolation layer KB would be much smaller than Ks, the superstructure stiffness? These are the assumptions for base isolated structure. Now, do we have this or not? We say that the base isolation layer is much flexible compared to the superstructure, right? In a base isolated structure. Okay. So this assumption is okay. Okay. For a base isolated structure, the base isolator stiffness is much smaller than the superstructure stiffness. So, okay, that's why if you consider the equation for omega S and omega B, I can say that superstructure frequency would be much larger than the overall base isolated structure frequency, or vice versa, time period of the base isolated structure, so time period of the superstructure would be much smaller than time period of the base isolated structure. Okay, this M is not negligible, it is comparable to MB, or mass of the base mat is not negligible, it is so maybe I should write it like MB. MB is of the same order of the superstructure. So the total mass, which is M plus MB, okay, total mass M plus MB, okay, this is actually not negligible, or like, you know, there is not a magnitude of order difference between this and any other quantity. Basically what we define a term gamma, let us say, which is the ratio of the mass of the superstructure by total mass, where total mass is M plus MB. So we can write this as M plus MB as well. Okay. And this is not negligible. However, okay, so I can say that M and MB are comparable, but typically KB is much smaller than KS. So that's why I'm able to make this assertion, assuming that mass are almost of the same order, but stiffnesses are much smaller. Because I mean, imagine superstructure, unless it's like a very flexible, let us say steel building, very tall steel building, and the time period is above 1 second or something like that. If you have any structure, the typical time period is less than 0.5 second, or let us say 0.6 second. Okay, and the base isolated time period is typically like, you know, above 2 seconds. Okay, so if I can make this claim, let me define, okay, a parameter epsilon, which is the ratio of base isolated frequency to the superstructure frequency and the square of that. Why I'm doing that, I'll come back to that, because what happens when I start solving this equation, I tend to get these terms, epsilon, which is the ratio of those frequencies, and gamma, and then I need to have some idea of the estimate that what are the order of these terms, so that if I have to neglect some terms, I can make an informed decision based on these. Now, if omega B, which is the base isolated frequency, okay, if it is much smaller, or the omega S, which is superstructure frequency, it is much larger than the base isolated frequency, what we typically observe that this is of the order of 10 to the power minus 2 or smaller. So because now see, I'm comparing the square of the quantity. So if the initial it was 1 by 10 or 0.1, when you consider the square, that ratio becomes 10 to the power minus 2. I'm considering square because when I solve this multi-degree freedom equation, then I actually get terms like this, okay, square terms. Is this clear, everybody? I'm just defining these terms because I'm going to encounter them later when I solve this equation, and then it becomes helpful to know these equations. Okay. All right. So I have two terms, epsilon, which is omega B by omega S square, and then I also have gamma, okay, which is M by M. Okay. So how do we solve a multi-degree of freedom system? How do we get the frequencies? Eigenvalue problem. So what do we do basically? we take the basically determinant of this quantity here, right? K matrix minus omega square mass matrix, and the determinant of this we set it equal to 0, correct? And then we get equation in terms of omega, and the frequencies actually provide omega square. You can think it as eigenvalue. Whatever the values of frequencies we get provide the modal frequencies. So we can do that here. What was this? This was KB 0, 0, KS, isn't it? Our K was KB 0, 0, KS. And what was M here? Sorry, this would be omega square M, or I will write M plus MB. M plus MB, the first term is M plus MB. I'll just write it capital M, which is M plus MB here. Okay, so M, and the small m, and this is equal to 0. Okay, so basically the equation of motion, sorry, not equation, the characteristic equation that I will get. In fact, let me do this. Why don't you write it, the characteristic equation, and then solve? Remember, if you have an equation like this, okay, what is your x? Minus b plus minus b square minus 4ac divided by 2a, right? So take the determinant of this, get the equation. The equation that you will get, it would be in terms of omega is 4 and omega square. So it would be a quadratic equation in terms of omega square. Okay, please get that and try to get by making this, assuming this approximation epsilon and gamma, try to get omega 1 and omega 2. Okay, you will be basically getting the values of omega 1 and omega 2. You will see that, okay, that how these frequency are relating to the frequencies that we have defined here for 2 single degrees of freedom systems. Okay, so please do that. We're going to discuss that anyway, but it is important that you do that. So go ahead and try to solve, get first the characteristic equation and then solve it, and then utilize these approximation to see what do you get as omega 1 and omega 2 and how do they relate to omega s and omega b. Okay, it is a very interesting exercise actually for base isolated structure. You will see something like, very nice. Okay, let us see what do we get. I hope at least you got the characteristic equation. Remember, if I substitute this and then I solve this basically, okay, what I would get as my determinant as, this would be KB minus omega square m, okay, and then minus omega square m, the second element, minus omega square m, and this would be Ks minus omega square m, and this is equal to 0. Okay, and then I can multiply this and rearrange the term. Okay, and knowing that my gamma is actually m by m. Okay, I can write this as 1 minus gamma omega 4 minus omega b square plus omega s square times omega square plus omega b omega s square 0. So remember, this is a quadratic equation in terms of omega square. Okay, now further what we can do, or okay, let me just do this first, write down. So it is quadratic in terms of omega square. Okay, so my omega square I can write it as minus b. Remember, this is b here, so this would be omega b square plus omega square, because my b here is now this one, minus of this quantity, plus minus b square minus 4ac. This is omega square whole square minus 4 1 minus gamma omega square omega s square divided by, okay, 2a, and a is 1 minus gamma here. Okay. Now, in this case, if you take omega b square outside, okay, so let us say I take omega b square outside, I will have 1 plus omega square by omega b whole square plus minus, when I take omega b basically outside here, okay, what I will have to enter here is basically omega 4. So it would be 1 plus omega s, okay, or maybe what should I do here? Not do it like that. We had assumed omega b by omega s, right? So maybe I take omega s outside here. So let us do that. Okay. Let us take omega s outside. So this becomes 1 plus omega b by omega s. Okay. Plus minus 1 plus omega b by omega s square whole square minus 4, okay, omega b by omega s square, and this whole thing divided by 2 1 minus gamma. So this is omega s square. Now what is this term here? This is my zeta that we had used, right? So I will write it here. First let me write down all the terms, then we will start to make approximations. Okay, 1 plus epsilon square minus 4 1 minus gamma times epsilon divided by 2 1 minus gamma. Okay, so I will keep writing this as, let me take this outside, 2 1 minus gamma, and inside I will be left with 1 plus epsilon, and if I expand this would be 1 plus zeta square plus 2 zeta, or maybe I should write it like this, 1 plus 2 zeta plus zeta square, and this would be 4, sorry, I keep calling epsilon as zeta, this is epsilon, 4 epsilon plus 4 gamma epsilon. Okay. Now let us see what approximations can we make. Can I say in this case omega square 1 2 1 minus gamma, I have 1 epsilon, and this one as I have 1 plus, or in this case if I subtract this term and this term I would have 2 epsilon minus 2 epsilon, okay, and then plus 4 zeta, gamma epsilon plus this. Now remember we said that this quantity gamma is m by m, which is less than 1, but it is not a very small quantity. It is still comparable, right? We told that above. However, zeta is of order of 10 to the power minus 2. So zeta square would be order of 10 to the power minus 4. So very, very small compared to this. So utilizing that, I can perhaps neglect this. And then I have the term 1 minus 2 zeta, let us take that common, and it would be 1 minus 2 gamma. Okay. Now, what we can do in this case, okay, let me just, we have to now simplify this so that now we know that if I have something like this 1 plus x to the power n, a polynomial expansion of this one, if x is a very small quantity, can be written as 1 plus nx if x is very, very small, right? So we are going to utilize that as well. Okay, and then see what happens. Okay, so let us do that. So I have omega s square to 1 minus gamma 1 plus epsilon plus minus. This term is gone. I am remaining with this term here, and if I take the whole root of this one, it would be 1 minus half times this quantity here. Okay, and that will give me plus minus 1 minus epsilon 1 minus 2 gamma. Okay, now remember, my omega n square and omega 2 square would correspond to when I consider first the positive sign here and then the negative sign here. And I don't yet, right now I don't know yet which one correspond to what. So let us first take the positive sign and then see what do we get. Okay. The lower frequency would be the omega 1 and the higher frequency would be the omega 2. Okay, so this is omega square 2 1 minus gamma. I am considering positive term now, so it would be plus 1 minus zeta plus 2 gamma, sorry, epsilon plus 2 gamma epsilon. So this term will cancel off. What I will get here, omega square 2 1 minus gamma 2, okay, 2 plus one. So if I take 2 common, 1 plus gamma zeta. Okay. Now this will cancel off here and I will get as omega square 1 plus gamma zeta and 1 minus gamma. Okay. Now for this one, okay, I said that zeta is order of 10 to the power minus 2. Gamma is less than 1 but not very negligible, or not negligible, not very small. Okay, so can I say gamma zeta term can be neglected with respect to 1? However, the denominator term gamma cannot be respected with respect to 1, but gamma times epsilon can be. So this term again would be omega square divided by this term would become equal to, or not equal to, approximately equal to 1, and I have this here. So what I'm getting here is actually the higher frequency, so maybe this is omega 2 square. We will see that what do we get as the other term when I take the minus sign here. So omega 2 is omega s 1 minus gamma. Okay, now let us see when we take the negative term, then what do we get? When we take negative here, in fact, why don't you do this? Take negative here and see what do you get. Simplify like what I have done here and see what do you get as omega in the second case when you take the negative term. Should not take you much time. Okay, just do the similar kind of manipulation that I have done here and see what do you get. Okay, let us see. When I take the negative sign, I mean this expression would be omega epsilon times omega s square. Okay, so omega s square 2 1 minus gamma times 1 plus epsilon minus 1, and then this would become plus, so I should maybe put this whole thing inside bracket. Okay, this is plus zeta 1 minus 2 gamma. Okay, when I do this, I will get this as omega square 2 1 minus gamma. This will cancel off. I'll have this epsilon common, I will take it, and this would become 2 minus 2 gamma. Okay, so if I take 2 outside, it would be 1 minus gamma it would be cancel off here. Okay, 2 will cancel off and I will get omega square. Remember, this is omega square. Now this is omega 1 square. Okay, so this would become omega s square times epsilon. Now I know that epsilon is omega b square times omega s square, right? This is the value of epsilon. So if I substitute that here, what do I get? Omega square times omega b square times omega s square. Okay, so omega 1 square as omega b square. Okay, and omega 1 as, you just take the square root, would be omega b. What is omega b? What had we defined the omega b as? Omega b was frequency of the base isolated structure when considered as a single degree of freedom representation. Is it or is it not? And even when I solved a 2 degree of freedom representation of the same building, I am still getting my omega 1 as omega b and omega 2 as omega s divided by 1 minus gamma. Okay, so for a base isolated structure, even when you consider 2 degree of freedom representation, as long as these assumptions are valid, that your frequency of the superstructure is much higher than the base isolated structure, so that these are valid. The first mode is basically the base isolated mode. The second mode is the deformation in the superstructure, but the frequency is not exactly equal to omega s. It might be close to that, but not exactly equal to omega s. Okay, now is this an important conclusion or not? That even when you solve a 2 degree freedom representation, your first mode was coming, that is coming out to be equal to the base isolated mode, and the second mode is the deformation in the superstructure, because omega s is what? It is the frequency of the fixed base superstructure. Okay. Now you can go ahead, once you have the frequency, you can find out the mode shapes as well, right? That is not difficult to do, but we are not going to do that. I'm just going to write down the final answer. You can go and verify if you like. Your phi 1 would be mode shape, and this is the base isolated mode shape, 1 plus epsilon. Okay, and phi 2 would be, you will get as 1 minus gamma zeta divided by gamma. Okay, now as you know, this is what? This is phi 1 1, right? And this is phi 2 1. This is phi 1 2, and this is phi 2 2. Okay, so if I have to represent these modes, draw these mode shapes, how would that look like? Phi 1 1 is equal to 1 and phi 2 1 is equal to epsilon, where epsilon is a very small quantity, remember? Okay, so if I have to draw it, I will draw something like this. Small deformation in the superstructure. Compared to large deformation in the bearing or the isolation layer. Okay, so remember, we are measuring everything with this relative quantity. Okay, so this one is phi 1 1, which we have obtained as 1. This one is phi 2 1, which we have obtained as epsilon. Okay, where epsilon is a very small quantity. So in the first mode, what we are seeing here, the superstructure contribution is very less. Okay, the deformation in the superstructure corresponding to the first mode is epsilon, very small. And we can again go ahead and draw the second mode. What happens in the second mode? So phi 2, let me draw this. Remember, now phi 2, it is negative, phi 2 2. So it is in opposite direction to the phi 1 2. So it would look like something like this. Okay. This here is basically your phi 22, and this here with respect to the relative deformation of the base is phi 12. This is equal to 1, and phi 22 is basically the second quantity here. Okay, so in the second mode actually, okay, remember this is your omega 1 and this is omega 2. In the second mode, the superstructure deformation it's not negligible compared to phi 12. So phi 21 is not negligible compared to phi 12. However, if you try and go ahead and find out the modal participation factor, which you can do it by writing down the expression for the modal participation factors. Okay, so you can multiply the mode shape and find out. You would get this approximately equal to 1 minus gamma times epsilon, and this you will get as gamma times epsilon. Okay, and of course if you sum this up it would be equal to 1 because the sum of contribution of each mode should be equal to 1. Okay, but what I'm saying, in the second mode the contribution of the superstructure is not negligible compared to the contribution of this phi 12, which is the base isolation. However, when you calculate the participation factor of the each mode, you will see that first mode is actually approximately equal to 1 minus gamma zeta, which you can I not say that this quantity is very small compared to 1. So this is almost equal to 1. The whole participation is actually coming from the base isolated mode. Okay. Is that okay? So you have to, what we have derived here is basically, okay, the contribution, basically the frequency of each mode, which we see that it is coming out to be close to omega 1 and omega 2. Okay. And the participation of each mode. So the omega 1 was close to the base isolated mode. Omega 2 was not close, but the superstructure frequency. Okay. The participation of the base isolated mode is almost close to 1, and you have very less participation of the superstructure mode. This would only be valid as long as your approximations, basically, which we had assumed, E omega b by omega s square is very small, which means omega b by omega s. So as you can see that if you want the whole response to be dominated by the isolated mode, you need to ensure this. The frequency of the base isolated mode is much smaller than the frequency of the superstructure mode. And how we can ensure that? If we assume that basically the masses are comparable, we can ensure this, okay, by ensuring Kb is much smaller than Ks, so that isolation layer is very flexible. But remember, in the Kb, it is, omega b is actually Kb divided by m, and omega s is Ks divided by superstructure mass. So it is not exactly equal to omega b or not directly proportional to Kb. It also depends on this mass. Okay, but assuming that mass are comparable, not of the order magnitude of difference, as long as you ensure that, you can ensure that effectiveness of base isolation structure by ensuring that the contribution of the response mostly come from the isolated mode. Okay, is this clear? Anybody has any doubts? It's very important that you understand. You might have been discussing all about this, that contribution of the isolated mode, the first mode is mostly the isolated mode itself, but having a mathematical appreciation is also important, because then you can have an insight into the overall dynamics of a base isolated structure. Superstructure should be stiff. So typically we like, based on the observation and like, I mean, anybody who has designed or like, come through a lot of structures, they would know that for all the building structures, typically the period is between 0.2 second to 0.8 second or 1 second, let us. Now, for base isolated structure, we just want to ensure that it is spaced apart from that period. Okay. So if the structure period is 0.5 second, we go for at least 4 times that, let us say 2 second. Okay. So that my omega by omega s becomes 1 by 4. If I go for 0.5 second fixed, and so I've just reversed that one. Now this is what omega, no, this is omega by omega, and then this is 0.25, right? So what does my epsilon becomes? 0.25 square, which would be 0.0225, I think, right? Yeah, what will happen if we consider this? Now this would be 0.22. I think this would be 625. All right. So this is of the order of 10 to the power minus 2, isn't it? And basically, like, it's a design basically assumption, as long as you maintain in that period range, you usually get a good spacing between the, or basically contribution mostly from the isolation mode. Remember, this is M1 and M2 are basically what? These are modal masses. So maybe instead of writing it like this, I will write it like this one. L is your influence vector. So I would write it like this. Okay. So now you have a mathematical proof and the understanding of the assumptions that we make when we talk about the dynamics of base isolated structure. You should have complete idea now that how does the superstructure behave, what role does it play in the overall response, what do the frequency depend on, in order to ensure that the base isolated structure mostly behaves like a single degree of freedom structure, what are the assumptions that are required, all those things now should be known to you because now you have mathematical background of the same.